Have you ever just looked at the world around you and wondered, how does science make sense of all this beautiful chaos? Well, it's not magic. It's all about learning to speak a very specific language, a language built on precision, measurement, and a whole lot of honesty.
I mean, just look at this. You've got the brilliant colors of a rainbow, the sheer speed of a race car, the raw, untamed power of a lightning strike. How on earth can a single system describe all of these things in a way that's consistent and makes sense? Well, that's the incredible challenge that physics takes on.
So to even begin to tackle that challenge, we have to start with the most fundamental question there is. What exactly is physics?
And here's the answer, right at its core. Physics isn't just a big pile of random facts. It's a system, a framework for taking our questions about the world and finding organized answers. The whole point is to describe everything we see using just a few fundamental ideas.
Okay, so how do we create that organization? We need a common language. And in physics, that language isn't really built on words, it's built on something way more fundamental, measurement.
And right away, we have to get something really important straight. Counting something is perfect. It's exact. You have 3 apples, not 3.0001 apples. But the second you pull out a ruler to measure something, you've just stepped into the world of approximation. That desk isn't exactly 1.5 meters long, it's about 1.5 meters. And how good that about is? Well, that depends entirely on your tool.
To build this language of measurement, we need some foundational building blocks. In physics, we call these base quantities. A really good way to think of them is like the fundamental nouns of reality. These are the core ideas that you just can't break down into anything simpler. And here they are: length, mass, time, temperature, and electric current. Isn't that incredible? Pretty much every single physical thing you can possibly imagine can be described using some combination of just these 5 core concepts.
But, of course, just naming them isn't enough. For any language to actually work, everyone has to agree on what the words mean. That's where the International System of Units, or SI units, comes into play. This is what standardizes everything. Length is in meters, mass is in kilograms, time is in seconds. It's what makes sure that a physicist in Brazil and an engineer in Japan are speaking the exact same language.
All right, so speaking this language is one thing, but speaking it well, that's a whole other ballgame. And this brings us to 2 incredibly important and, let's be honest, often confused ideas: precision and accuracy.
Let's break it down. Simply put, accuracy is about being correct. It's how close your measurement gets to the real, true value. Precision, on the other hand, is all about consistency. It's how close your measurements are to each other, even if all of them are wrong. And that really brings us to the key question, doesn't it? What good is being super precise if you are precisely, consistently wrong? Think about it. A clock that's always exactly 5 minutes fast is incredibly precise, but it's not accurate at all. You'll just be consistently early for everything.
This dartboard analogy makes it all crystal clear. On the left, that's the dream. That's the goal. You are accurate and precise. All your darts are clustered right in the bullseye. But on the right, well, that's our fast clock. The darts are all grouped together really tightly, so that's high precision, but they're all way off center. That's a consistent, systematic error.
And here are the other 2 possibilities. On the left, it's just a total mess, right? Low accuracy, low precision, the shots are completely random. But the one on the right is really interesting. The precision is terrible, the darts are scattered, but if you were to take the average position of all those darts, you land smack in the middle of the bullseye. So the average is accurate, even if no single throw was.
Okay, so we have our base units, and we know we need to be both accurate and precise. But what happens when we get data that's in a different dialect, like, say, the imperial system? Well, we need to be able to translate. So let's try a real-world problem. Your car's speedometer says you're going 60.0 miles per hour, but in the official language of physics, the standard unit for speed is meters per second. So how do we translate one to the other?
The trick is to just break it down into simple logical steps. First, you deal with the distance. Convert miles into meters. Then, you deal with the time. Convert hours into seconds. And finally, you just divide your new distance by your new time. Simple as that.
And boom, there's our answer. 60.0 miles per hour translates perfectly to 26.8 meters per second. Once you know the process, you can move seamlessly between different systems.
But hold on, there is one more crucial layer to this language. If measurement is the vocabulary, then you can think of significant digits as the rules of grammar.
They are how we communicate honesty and certainty in our numbers.
Think of significant digits, or sig figs, as we call them, as a way of being totally transparent. They tell anyone who looks at your numbers exactly how good your measuring tool was. They're basically all the digits you know for sure, plus one last one that you kind of had to estimate. It's what stops us from pretending a measurement is more precise than it actually is.
And when we do math with these measurements, we have to follow some rules, but the main idea is really simple. Your answer can never be more precise than your weakest link. So, if you're multiplying or dividing, your answer is limited by the measurement that has the fewest significant digits. If you're adding or subtracting, it's limited by the number that's the least precise after the decimal point. It's all about not claiming you know more than you actually do.
And that really gets to the heart of it all. No measurement is perfect. Every single one, every tool, every observation has a fundamental limit on its precision. We can always build better tools, sure, but we can never ever reach absolute, infinite perfection.
So, here's the big takeaway. The language of physics is way more sophisticated than just a jumble of numbers. It's a whole system designed for crystal clear communication. It lets us share what we've learned about the universe while also being completely honest about the limits of that knowledge.
Which, leaves us with a much deeper question to chew on. We've just established that every single tool we use to look at the universe has limits. Every measurement is just an approximation. So, if the very language we use to describe reality is built on this foundation of uncertainty, what does that imply about our scientific quest for some kind of absolute, final truth?